Hello everyone listening Radio Khanchi 90.4 FM हम सबका रेडियो. I am Dr. Rajiv Asthana, Associate Professor, Gosno College, Ranchi. Today I will discuss Gibbs paradox, which is in Statistical Mechanics paper of 6th semester UG and 3rd semester PG course of Ranchi University. Gibbs paradox arises from an incorrect traditional definition of the entropy. Among its flaws, the traditional definition predicts a violation of the second law of thermodynamics. By adopting Boltzmann's definition of the entropy, the violation of the second law is eliminated and Gibbs paradox vanishes. In the context of application of statistical mechanical analysis to the process of mixing two ideal gas samples, we come across Gibbs paradox. The different values of entropy change associated with the process of mixing of two ideal gas samples in the following two cases. First, the two gas samples contain the same species. Second, the two gas samples contain two different species, give rise to Gibbs paradox. In the diagram, the first one shows the mixing of two different species and the second one shows the mixing of same species. A schematic representation of the mixing by diffusion between two gases is shown below. Case A shows mixing of two gases each made of different particle species. Case B shows mixing of two gases made of the same particle species. By applying statistical mechanics to the motion of particles, that is molecules, and the distribution of energy among the particles contained in a system, Boltzmann developed the equation S is equal to log W plus S naught. This equation connects entropy S of the system to the probability W of a macroscopic state corresponding to a given macroscopic equilibrium state of the system. In the formula, S naught represents entropy at 0 Kelvin. Boltzmann didn't assign any value to it. Planck modified the equation by introducing the constant K, which is called Planck's constant, and setting S naught is equal to 0, and wrote S is equal to K log W. Gibbs found that this equation, when applied to the calculation of the entropy of an ideal gas, led to the results that showed Boltzmann's statistical entropy was not the same as thermodynamics Clausius entropy. Gibbs gave a resolution of this by proposing a correction to the method of counting the number of microstates that corresponds to a given macrostate to obtain the value of W of a system of two ideal gases when the particles in the two gases are distinguishable or are indistinguishable. The partition function of a perfect gas is represented by the formula Z is equal to V upon H cubed bracket 2 pi mkt to the power 3 by 2. This is our equation 1. The entropy of a perfect gas is represented as S is equal to Nk log Z plus 3 by 2 Nk. This is here equation number 2. Now we put the value of Z from equation 1 in equation 2. We will get S is equal to Nk log bracket start V upon H cube 2 pi mkt to the power 3 by 2 bracket closed plus 3 by 2 Nk. This represents equation 3a. Now this equation can also be written as S is equal to Nk bracket start log V plus 3 by 2 log M plus 3 by 2 log T plus C bracket closed. This is equation 3b. In this equation, the C represents a constant which includes H and K. The entropy given by this equation 3b does not satisfy the additive property, thus gives paradoxical results. We consider two systems denoted by A and B held at same temperature. TA equals TB equals T, suppose, and the two systems are partitioned by a barrier as shown below. On the left is system A, on the right is B. The symbol N represents total number of particles, V represents volume, T represents temperature, M represents mass, and capital S represents entropy. If the particles of the two systems are different, then using equation 3b, we have SA is equal to NAK bracket start log VA plus 3 by 2 log MA plus 3 by 2 log T plus C bracket closed. Equation 4a. SB is equal to NBK bracket start log VB plus 3 by 2 log MB plus 3 by 2 log T plus C bracket closed. Equation 4b. As the entropy is an extensive quantity, it must satisfy additive property. Now the partition is removed and the gas molecules are allowed to mix freely. Hence the entropy of the joint system will be written as SAB is equal to SA plus SB. Now putting the values of SA and SB, the equation becomes SAB is equal to NAK bracket start log VA plus 3 by 2 log MA plus 3 by 2 log T plus C bracket closed plus NBK bracket start log VB plus 3 by 2 log MB plus 3 by 2 log T plus C bracket closed. This will represent equation 5. If the particles of these systems are same, then VA is equal to VB is equal to V, NA is equal to NB is equal to N. Equation 6. Then the entropy of the combined system will be written as SAB is equal to SA plus SB equals 2NK bracket start log V plus 3 by 2 log M plus 3 by 2 log T plus C bracket closed. Equation 7. Now we shall find the actual entropy of the combined system. Let the partition be removed to allow the molecules of the gas to mix freely. So there will be 2N particles in 2V volume. Hence the entropy of the mixed system will be S dashed AB is equal to 2NK bracket start log 2V plus 3 by 2 log M plus 3 by 2 log T plus C bracket closed equals 2NK bracket start log B plus 3 by 2 log M plus 3 by 2 log T plus C bracket closed plus 2NK log 2 equals SA plus SB plus 2NK log 2. This will represent equation 8. So we see that equation 8 and equation 7 are not the same and they differ by 2NK log 2. This shows that entropy has increased by 2NK log 2. This value is called entropy of mixing. This shows paradoxical result, and this is known as Gibbs paradox. Now let's see how Gibbs paradox can be resolved. Gibbs solved this paradox by considering the two systems as same, so the gas molecules are identical and indistinguishable. The gas molecules cannot be labeled now, so we should apply the idea of indistinguishability. While the mixing of two samples is in progress, N molecules of each system cannot be distinguished in factorial n ways. Hence, to arrive at the correct result, we must divide the weight of the system by factorial n. Hence, the statistical weight of the system will be written as W is equal to factorial capital N pi symbol gi to the power ni upon factorial small ni total divided by capital N factorial. This is equal to symbol pi gi to the power ni upon factorial small ni. Hence the entropy of the perfect gas can be written as S is equal to Nk log bracket start V upon H cube 2 pi mkt to the power 3 by 2 upon capital N bracket closed plus 3 by 2 nk, or S is equal to nk log bracket start V upon n within bracket 2 pi mkt upon h square to the power 3 by 2 square bracket closed plus 5 by 2 nk. This represents equation 9. Hence, after mixing, the entropy of the combined system will be written as SAB is equal to 2nk log square bracket start 2v upon 2n bracket 2 pi mkt upon h square to the power 3 by 2 square bracket closed plus 5 by 2 into 2nk. That is, SAB becomes equal to 2S, that is equal to SA plus SB. This is equation 10. Hence, entropy represented by equation 9 satisfies the additive property as shown in equation 10. This shows that Gibbs paradox is resolved. Now, in this slide, we are showing the derivation of Sackur-Tetrode equation. The Helmholtz free energy F in terms of partition function Z is written as F is equal to minus kT log Z. So we will put the value of Z here. So capital F is equal to minus kT log small f to the power n upon factorial n, where small f represents capital V bracket start 2 pi mkt upon h square bracket close to the power 3 by 2. Using Stirling's approximation, log factorial n is written as n log n minus n. So we will get capital F is equal to minus kT bracket start log small f to the power n minus n log n plus n is equal to minus kT bracket start n log f minus n log n plus n bracket closed, or capital F is equal to minus nkt log small f by capital N minus nkt. Now, as entropy S is equal to minus del F by del T at constant V, therefore S is equal to minus del over del T bracket start minus nkt log small f by n minus nkt bracket closed is equal to nk log small f by n plus nkt del over del T log small f by n plus nk is equal to nk log small f by n plus nkt del over del T log V upon n within bracket 2 pi mkt upon h square bracket closed to the power 3 by 2 and square bracket closed plus nk is equal to nk log small f upon n plus nkt 1 upon v by n 2 pi mkt upon h square within bracket to the power 3 by 2 into v by n, then within bracket 2 pi mk upon h square to the power 3 by 2 into 3 by 2 t to the power half plus nk. So, after further simplification, we will get S is equal to nk log bracket start v upon n nh cube within bracket 2 pi mkt to the power 3 by 2 small e to the power 5 by 2 square bracket closed. This expression represents Sackur-Tetrode equation. So here I conclude this lecture. Thanks a lot for listening it. Thank you.